Hello and welcome to Module 4 of our R for Biologists workshop. Today we're going to be talking about the R programming concepts that Aola has covered in Modules 2 and 3. We're going to be doing a brief review of those and introducing some practice problems, and at the very end, a bonus challenge, which you can choose to complete if you want. But the main point of today is to make sure that everyone feels comfortable with these techniques and feels like they're on the same page. Because if you can get past this point, if you can get past the basics of R programming, then there's really no end to what you can do with R. But if you can't get past this point, there's nothing you can do with R. So this really determines whether or not you're going to be able to use R at all. So I want to make sure that we take this time to slow everything down, go through things step by step, and answer any questions that you have, because it's just so important that everyone feels comfortable with what we've talked about so far. So just to start off with, does anybody have any questions about the topics we've covered so far, or any issues they run into in their code, anything like that that they'd like to bring up before we jump in? And bear in mind that if you do have a question, you're absolutely not going to be alone in that. So I want everyone to feel comfortable saying if they have a question, because this stuff is really difficult. And I guarantee you someone else is having that same question that you have and hoping that you'll ask it. Okay, well, do feel free to ask questions as, okay, so Manish asks, what exactly does in do? Yeah, that's actually that's a really good question. So in is only used in if-else statements typically, or in for loops or something like that. Yeah, for loops. So when we do a basic for loop, so if I say, my words, worlds. So these are my words. And if I say for word in my words, print word. So this might be some simple for loop you can use to loop through your vector of words and then print each one in turn. And so we can see it's doing that quite effectively here. So the in operator is a very interesting operator in R that only really applies to for loops, because what it's essentially doing is every time you loop through, it is taking the next element of my words and assigning it to the variable word. So in the first loop through, word gets assigned as the value hello, which is the first value in our vector. And then it gets assigned as the value word, which is our second element in the vector. And so that's what in is doing. It's allowing you to do this loop, and then in is what assigns word as that value. So I know it's a bit convoluted. You don't really use in anywhere else. And so it becomes kind of this interesting thing that you really only see in for loops like this. Yeah, so the value of word changes with every loop. That's exactly right. Yeah, so in the first loop, the value is hello, since that's the first element. In the second loop, the value is word, since that's the second element, and so on and so forth. And so if I wanted to, for example, say if word is equal to world, print, this is the word I was looking for. So this is kind of a silly example. You'd never actually do this, but if word happens to be assigned to world, we're going to print this statement. And you can see first pass through the data, it's not assigned to world. Second pass, word is assigned to world, and therefore it equals world, and therefore it prints this statement. Third pass through the data, it's assigned to an exclamation point, so it doesn't print it. Okay, does that, Manish, does that answer your question there? Okay, great. Yeah, it's definitely confusing at first because one of the quirks of for loops is that you've got a variable that's constantly being assigned and reassigned for every element and every loop through that you do. Okay, what does string split do? I didn't understand it in DataCamp. So that's one of those special functions. So let's do this here. I can show you my sentence. So let's say that this is a sentence that I'm interested in doing a string split on. So if I start typing str split, so just notice that the very first thing that happens as you start typing this in RStudio is that it gives you a nice description here of what it's going, oh, sorry, a nice description of what it's doing. So just keep that in mind that if you're not sure what a function's doing, just starting to type the name will actually give you some information about it. So it says split the elements of a character vector X into substrings according to matches to substring split within them. Okay, that is probably kind of convoluted sounding. Let's do this. I'll show you something else that you can do in order to understand what a function is doing. If you come down to your console here and you type question mark, you don't have to do this in the console, it just tends to be more convenient. If you type question mark, the name of that function, and hit enter, it'll bring up the help page. And what that's going to do is it's going to offer more information, it's going to offer details, and it's going to offer examples. Okay, so this is a pretty nice example here of what this is doing. So if I take this example and I copy it, this is actually kind of a weird example. All right, if I take that and I copy it into the console and I hit enter, we can see what it's going to do here. So it's going through and it's taking the first. Okay, this is a bit overly complicated example. Let's just do the simple example. I don't want to overwhelm you guys. So let's say that X in this case is my sentence. This is what we want to split. Let's say we want to split it based off of space. Okay. So let's go ahead and run that. So you can see here what it's returned. It's returned a list that contains, this is the word I was looking for. Okay, let's actually assign this now to something. So like I said, it returns a list. And if we take the first element of that list, we can assign it to split vector. We can see here that it's now a vector. So what has this done? Can anyone tell me what, in simple terms, split string did here?
It separated each word into a different vector.
Right, it did, but right. So it broke up the sentence
based on the space. Yeah.
Exactly, based on the space. Exactly. So
I mean, you could have used something else, and that would do it too.
Exactly. So let's say that instead I used O as the space. So we can see now that the split vec is split not by spaces anymore, but by the O character. Exactly. And so this is one string. It's one contiguous sentence. And we've taken it and broken it up into a vector that contains 5 elements based off of the split that we specified, which was an O in this case. This is a very useful function that you'll probably never use because there's actually more efficient ways to do this, but it's certainly a good way to learn it at sort of a basic level, how this is working. Okay. Now, the point of it returning it as a list is because you could actually supply multiple things. So if instead I supplied my sentences, and let's say that that includes this sentence, and it also includes this sentence, you know, this is the word I was looking for, and this is not the word I was looking for. Let's give that instead as the argument. Now we can see it's a list of length 2. And that's because it did each of those, each of these characters or these strings separately and returned them separately as elements in the list. So we can see here, this is the word I was looking for with all the O's split out, and this is not the word I was looking for with all the O's split out. Okay. So, all right. So before we jump back into the review, were there any other questions? Okay, well, do feel free to ask at any point. I'm happy to pause, and that way we'll make sure that this is part of the video later as well. All right, so we talked about simple data structures. Now I'm going to go kind of quick through this. We talked about numerics, logicals, and characters. So numerics, as you'll recall, those can be integers, they can be floats, which is where you have a decimal point. That's just another way of saying that, or doubles, which is, again, just another way of saying you've got a decimal point. They can be in scientific notation like you see here. And we generally use these for any sort of operations involving math or indicating positions in a data frame or a list, that sort of thing. Logicals can be true or false, so they're pretty simple. Something that you might not know is that if I run these lines of code, I see true and false here. If I just put a capital T and I run that, what do you think that will do? Does anybody know what will happen if I just run a capital T by itself as a line of R code? Do feel free to actually try this if you've got this pulled up, which hopefully you all do. Okay, so Lorena says it'll print true. All right, let's find out. And it does. Yeah. Okay, Mustafa says same. Yeah, it does. It prints true. And that is because capital T and true are actually the same things. You can use capital T as a shorthand for true. It's not particularly advisable because it kind of makes it harder to tell what your code is doing if you just have a T. But it is something you can do. False works the same, just a capital F will give you false. Notice though that if I try to put TR, that doesn't do anything. So it's got to be T or true, or F or false. Okay, well, I'll leave these here. Characters, so we talked about these. These hold string data. Pretty basic. Anything that's between double or single quotes will be a character. Okay, so let's look at some methods for simple data structures. So you can see the class of any object in R. And like I'm saying, like numerics, logicals, characters, these are all types of objects. So just keep in mind, everything in R is an object. And when you're looking at these, even though it's just a single number, it is an object in R. So just bear that in mind. Just like vectors or data frames or classes later on we'll see, or functions, everything is an object. And everything is an object also means that everything has a class, because all objects have to have a class. So let's see what the class of the object hello world is. It's a character. Okay. Class of 1, numeric. Class of true, logical. All right. So does anyone recall what the class of class is? Like this. I think that was right. Does anyone recall what this will give back? Okay. Lorena says function. Okay, yeah, good. It is a function. And that's because class is actually a function. And just like everything in R is an object, functions are also objects that have the class function. Okay, so structure is a function that will allow you to see not only the class of an object, but also some basic information about what it contains. So we can see this says it's a character. CHR is shorthand for character in R, and it contains the value hello world. This is a numeric. NUM is short for numeric, contains the value 1. This is a logical. Logi is short for logical, contains the value true. All right, so does anybody have any questions about what we just talked about here? About the whole idea of everything being an object and class and structure and that sort of thing? Okay, well, do feel free to put questions if you have them in the chat, and we will circle back later. So arithmetic is some of the most, okay, good. So arithmetic is some of the most basic sort of operations you can perform with these simple objects in R. So if you've got two numerics, you can easily add them together using the plus, subtract them, multiply, and even do the modulo, which is kind of a fancy way of doing of finding the remainder from a division. So 10 divided by 3 leaves a remainder of 1. And that's why you see the remainder is 1 here. Does anybody know what I'll get if I do 14 modulo 3? What will be the results? Okay, yeah, exactly. It'll be 2. Because when you divide 14 by 3, you get a remainder of 2. Okay, so let's move on to some logical operations now. So if you've got a logical true or false, you can easily negate it by putting an exclamation point in front. So if I've got true, the exclamation point in front of true means not true, which is another way of saying false. So if I run this, I get false. And if I run this one, I get true. Just as a reminder, when I'm running these lines of code, I'm just hitting Control Enter to run the line and advance it. So just hit Control Enter to do that, or Command Enter, I think, if you're on Mac. Some other things we can do is we can use operators that allow us to perform some basic sort of syllogistic logic with R. So I'm going to show this here. We're going to use the AND operator here to do this. So let's say that I've got two variables or two assertions, went to the store and bought cheese. So both of these are true. Basically, I'm asserting here, I went to the store. That is true. I'm also asserting I bought cheese. That is true. What about the assertion went to store and bought cheese? What if I want to assert that? Well, how could I do that? I could easily do that by just saying went to store and bought cheese. Some sort of basic formal logic here, but this is how you do an AND operation in R. So if I run this, I can see that the value of this new assertion, went to store and bought cheese, is true. The reason is because both sides of the assertion were true and there was an AND operator. ANDs are always true when both sides are true. what will happen if I change one of these to false? What will went to store and bought cheese evaluate to? Right, exactly. It'll be false. That's because both sides have to be true for the whole thing to be true when you're working with an and statement. Okay, so let's talk about another one that we might want to evaluate here. Got up on time or took the bus. So to say or in R, you said, oh, go ahead.
Quick question. I tried to type F instead of false, but it didn't work for me for some reason. When I typed false, it worked.
Did you use an uppercase F?
Yeah, I did, I think, yes.
I'll
try again later.
Okay, yeah, I think there might be some other mistake going on there. Yeah, because that should work. That's a pretty fundamental R programming thing. Unless you've got a newer version of R where they took that out, but I've got 4, so I think that should probably work. Okay, so let's take a look here. So it says I got up on time or took the bus. Okay, does anyone know what this will evaluate to? What will be the result of this assertion? Yeah, it'll be true. And just to make this a little bit clear, because I think this was confusing for a lot of people at first, an or statement is not an exclusive or statement. It can be the case that both of these are true or only one of them is, and it will still all evaluate to true. The only thing that it can't be is both of them false. If both of them are false, the whole thing will be false, but that's the only way that you can make it false when you're talking about an or statement. If it was an exclusive or statement, then if both of them are true, that would also still evaluate to false, because exclusive or, only one of the two can be true. We don't typically use exclusive or, though, in R programming, or at least not that I'm aware of. So you can see this here. If I evaluate one of these to false, then the whole thing is still true. Okay, Simon asked, does R have a NAND operator? So I don't know if they have an explicit NAND operator. I think that you just use I think you just kind of do one of these, you know, kind of like this. It's kind of not and. How did you get the line between time and took? Well, that should be on your keyboard. There's a... Oh, yeah. Sorry there. Yeah, same key as the backward slash. Exactly. Yeah. Sorry, my cats are like tearing up something. Okay. All right. So let's ask another question now. Did you get flowers and potatoes or bread? So this is kind of a more compound statement here. What will this evaluate to? I'm going to see if you guys can figure that out. Okay. Yes, exactly. All right, good. So it will evaluate to true. All right, and that is because, as we've already mentioned here, this part, while this part is going to be false because flowers is true, but potatoes is false, therefore the whole thing is false. The whole and statement is false. It doesn't matter because bread is also false. And since we negated that, that means that the right side is true. And as long as one side is true, the whole thing will be true. Exactly. So a little bit of formal logic there for you. You don't have to worry about this. We don't really ever get more complicated than that when it comes to R programming. Just good to know how it's working. All right, so just in reviewing this, we know that the AND operator is true only when both sides are true. The OR operator is true when at least one side is true. Okay, so does anybody know how the double AND operator works? Has anyone seen this before? Anyone want to explain this? Okay, so I'm going to run line 86, and I want someone to see if they can actually let's do this. Let's run it like this. Can anyone tell me what line 86 here would give me? I just want to illustrate the difference between the single and the double ampersand. Does anybody have an idea what this will produce? We're including hello world in a logical operation here. So okay, so Diane says that operations only possible for numeric, logical, and complex types. Yeah, exactly. If we try to run this, we get an error. And that's because hello world is not a logical, and you can only do these operations on logicals. Let's run line 87 now. Okay, so can anyone tell me why line 87 works, but line 86 doesn't? Does anybody know what might be happening there? No, it does work. Line 87 does work. You can see it doesn't give an error. It just says false. All right, what happens if I take this and I move it right here? This will give you a little bit of a hint, I think. Now it gives an error. So why does this give an error when this doesn't? So I'm gonna put these in here just so you can see them side by side. Is error. Okay, so the reason is because when you're doing double ampersand logical comparisons like this, it goes from left to right in order up until it reaches a false. Okay, so it does true and false, gets a false, okay, and then it never makes it to the end because it's already gotten a false here from the first operation. Now, the single ampersand evaluates all of the comparisons at once. So it will evaluate false and hello world at the same time as it evaluates true and false. But the double ampersand goes from left to right. So given that, can anyone tell me why line 89 also errors when line 88 doesn't? Or can anyone explain to me what's happening there? Yeah, so it gives you an error, but can anyone tell me why? Why does this give an error when the same thing with ands wouldn't give an error? Is it comparing it to the first element? So it's doing this comparison, and then it's doing this comparison at the end. Yeah, this is just, no, like I said, when you've got the double or the double ampersand, it's just evaluating it from left to right instead of doing it all at once. So to have it in the single version, it would be, no, you don't need to have any of them be true. In fact, if I just replace this with false, it's perfectly fine with that. None of them need to be true. None of them need to be true. The whole thing can be false. So the reason that this errors, but this doesn't, is because when you evaluate, or sorry, that this doesn't error, but this does. Sorry, I said that backwards. This one doesn't error. This one does. The reason is because when you're evaluating this one, it goes from left to right. It says false and false. It finds that that is false. Okay. So therefore, once it reaches this final ampersand comparison, it already knows the left side of this equation is false. And therefore, there's no need to do this final comparison, because with an and, if one side is false, the whole thing is false. So there's no need to do that comparison now. So it doesn't. It just skips it, and it returns false for the entire statement. For this one, though, as we know, in an or statement, as long as one side is true, the whole thing can be true. Therefore, when we get here, we know that the left side is false, but we don't yet know if the right side here will be true. And so it does the comparison to actually see if possibly this right side is true. And in doing that comparison, it finds that this is not illogical, and it produces an error. So in this situation, there was no need to actually do the comparison. In this situation, because it still might have been true if the right side was true, then there was a need to do the comparison. Yeah. Like I said, there's no requirement that any of these are true, though. Like I said, if all of these are false, if all of these are false, if everything is false, it all still works. You won't get an error. So no, I just want to make sure that's clear. Yeah, that was gonna be my challenge question there, actually. So yeah, okay. So if you wrote it like this, thank you for that. No, this is good. If you put, oh, okay, sorry, I maybe I misunderstood your question then. So if you put a true here instead, what will this give? Well, Udayan said it'll give true, and that's correct. Because once we get to this last comparison, because the left side is true, we don't need to do this anymore, because it doesn't matter what the right side is. The whole thing's going to be true because that left side was true. Pretty cool. You know, there's good reasons to use this. There's good reasons not to use this sometimes. For example, if you have an if-else statement and you don't want to evaluate the right part of it until something else happens, you can use these to kind of control the order in which things get evaluated and save yourself a little bit extra time or space. Ultimately, not super necessary most of the time, just kind of important to understand what the distinction is. Okay. Does anybody have any questions about this before we move on? I'm burning through my time a little bit here. There's a chance that we'll go a little bit over time. I'm going to try to not have that happen. I do want to make sure we get to all your questions. So if you have to leave at some point, you're welcome to do that. I just want to make sure that we're taking the time we need to address, any issues that people are running into. Can we mix? Yeah, you can mix. You can mix and match them as much as you want. There's no limit. You can, put a. Here's a new challenge question. What will this give me? What will happen if I do it like this? 。 Yeah, false. Exactly. Because it's going to evaluate this part first. Because it's an and now, both parts have to be true for the whole thing to be true. Therefore, one part is false, so the whole thing is false. Therefore, we actually have to run this final comparison to see if the right side is true, just because, R wants to be thorough. And that's where we now run into the, oh, wait, hold on a second. No, no. Yeah. So sorry, I should have said it's not, the whole thing's not false. The whole thing's an error because the left side is false. Therefore, you have to run this comparison, and therefore it's going to find the problem on the right side. If anyone saw me do that just now, if you highlight a section of R code and hit Control Enter, it'll run whatever you've highlighted. Just in case no one caught what I just did there. Okay. Anyways, so does this make sense? Does anybody have any questions about this? Okay. All right. Let's go on to equivalence comparisons. So we're basically just asking this question, is the left side equal to the right side? In this case, we're saying, does 1 equal 1? And it does, so it's true. Hello equal to world, false, because these are different things. Hello and world are different. Non-equivalence is a way of saying something is not equal to something else. So 10 not equal to 1, well, that's true, because they're not equal. 10 greater than 1, true. 10 less than 100, also true. Sort of basic math comparisons here. 2 less than or equal to 2, pretty basic. 5 greater than or equal to 3. Okay. Does anybody have any questions about anything we've covered so far before we jump into these more complex data structures? I'll ask a quick challenge question here. Should have made this simpler. All right. What will this give me? What will be the result of this? I put this backwards. Yes. I meant for this to be a -1. This is fine. This is fine. Yeah, it's all false. All right. All right. What about if I make this a -1? Will it be false or true? Yeah, it'll be true because this left side will now be 4 and the right side is also 4. And then greater than or equals means it's going to be true. All right. What about if I take away the parentheses? What will be the result? All right, let's go ahead and run this. Still true. The order of operations changes. So the left side is now equal to 8 because the parentheses were taken away, but it is still greater than or equal to 2 to the second power. Probably could come up with a better example, but that's all I had on the fly. So hopefully that's all making sense. All right. Any questions or anything else before we move on? Okay, so Manish asked, how can the multiplication sign and the negative sign be together like that? The reason is because this is being used as like a negative, whereas this is being used as like a minus. So if I actually, let's see here. Oh, that does still work. Oh, that's crazy. Yeah, R can do some magical thinking sometimes. So R is one of those languages where it tries to think for you, and it tends to like do things that don't necessarily make sense because it thinks you wanted something a particular way. This is one of those times, actually. So if I have times minus 1, it's going to interpret this as me saying I have a -1 here, because when it does the interpretation of this line of code, it finds this pattern and it says this negative is supposed to be associated with this number. Now, if I took out the minus, or if I took out the multiplication, you can see here, it treats it like a normal minus because it now thinks that's what I want. So not necessarily ideal, but you can see here kind of how it's thinking. Yeah, it's cool. It's cool. You can run into problems though later. It's really, in some ways, it's better to have a programming language that does not try to think for you than one that does. Okay. All right, let's yeah. Oh yeah, Simon says give C a try. You'll wish for R's thinking. Yeah, actually, that's probably a pretty fair point. I don't want to have to think that hard, actually. Maybe it's okay for R to think for me sometimes. Yeah. All right. So let's go ahead and move on here. So we've got complex data structures. So variables are essentially objects that we create in R to hold the value of another object. So if I assign 1 to the object A, the variable A, I can see here I've created this A object and I've assigned 1 to it. Same thing with B, and now I can use these A and B because they hold the objects that I want to add together. I can just add A and B together rather than adding 1 and 2 together. This is a way to abstract away from your sort of numerical level here. This is a way for you to do more complex operations without having to actually write out all the numbers, by themselves. It's also a way for you to use things like for loops and if-else statements and functions to do more complicated coding that doesn't have to involve you managing directly those values. Okay, so variables in R can also have names, and so I can assign the name hello world to the A object here. And so now 1 has the name hello world. So at some point, we'll do an advanced R course, and you'll actually see that all the stuff I'm saying right now has a giant caveat, which is that none of it's really true. And in reality, you're not actually doing any of the things I'm saying you're doing, because what's actually happening is more interesting and more efficient than actually assigning variables and actually giving them names. But for simplicity's sake, this is all true. And I'm not lying at all when I say that this is how it works. Okay. So at some point, we'll have a more advanced R course where we talk about how this is really working under the hood. For now, let's talk about vectors. So vectors can contain a single type of object in R, and they can have multiples of them. So here you have a vector of numerics, 1, 2, and 3. Here you have a vector of characters, hello world, exclamation points, and here you have a vector of Booleans, or logicals, true, false, and false. As I just said, you can't mix and match. So let's say I tried to have a vector of 1, hello, and false. What will this give me? it'll give me back a character vector that includes 1, hello, and false, all as characters. And that's because you can't have in one vector, you can't have mixed data types. They all get converted to characters if there's a character present. If I took out hello and tried to run this, it gets converted all to numerics. So false, when it gets converted to a numeric, is represented as a 0. But if there's a character present, everything gets converted to characters. Again, R thinking for you. Don't love it, but just so you know how this is working, it's kind of important to understand this. Okay. In general, when you use vectors, you'll be doing it with one data type in the entire vector. All right. So you can make a numeric vector with this shorthand. This basically says all the numbers between 1 and 10. There's actually another way to do this, which is to use the seek command. Just does the exact same thing. Although in modern R programming, people actually tend to prefer when you use this. All right, vectors can have names. So every element inside your vector can get a name. So if I assign hello world exclamation point as the names of my vector, I can now see 1, 2, and 3 have the names hello world exclamation point. Okay. You can also access the elements of a vector using numeric indices. So here I'm getting the first element of my vec, which is hello. Now I'm getting the first through the second elements of my vec, which is hello world. Or because there are names in here, I can use the name as an index to get the value associated with that name. In this case, I get 1. So there's multiple ways you can access this. And having the naming feature for these vectors kind of adds a convenience to where if you manipulate something and you want to find out where a particular data point is, if you named it, even if the order got changed, you can find where that data point is. Okay. Does anybody have any questions about vectors before we move on to data frame? Okay. There's one more thing that I guess I'll leave you with because I think it's kind of interesting and it will give you a brief glimpse into how R actually works. But let's say that I assign 1 to A. Okay, so A is a numeric now. If I look at the first element of A, it says 1. So bearing in mind that we typically use this for accessing vectors, you can actually use this on single numerics. Likewise, if I look at the class of A, I can see it's a numeric. And if B is 1, 2, and 3, and I look at the class of B, I can see it also says it's a numeric. We've said up until this point that you've got simple and complex data structures. You can have A, which is a simple data structure containing only one numeric, or B, which is a complex data structure that is a vector of numerics. Yet they still have the same class. And you can access them the same way. How can that be? Well, I'll leave you with the actual answer, which is every string and every numeric and every logical is just a length 1 string, numeric, or logical vector. So if I have, A of, A1, this is actually equivalent to me doing this and making a length 1 vector. They're literally identical. So whenever you see something that looks like this, or something that looks like this, or like that, just know that that is actually a vector. It is a vector of the class logical, numeric, or character. So it's getting a little bit heavy there, but just wanted you to know that under the hood, that's actually what's happening. And when we said that there were simple data structures, that was actually a lie. It's a lie that we use to kind of make things simpler, but you'll learn over time that it's actually not true. And there are circumstances where it's important to know that that's not true. For what you're going to do in this workshop, though, not important to know. Just wanted to give you that information so that when you start to learn that and see that later on in your advanced R work, you'll understand what that means. Okay. Does anybody have any questions about this before I move on? Okay. All right. So let's go ahead and take a look at data frames now. So data frames can hold a mix of data types. It can have numerics, logicals, and characters. So if I go ahead and make a data frame here, okay, just to back up, when you make a data frame, you can use this data.frame constructor, right? So this is a way of constructing an object based on the class data frame. Okay, so you're constructing an instance of the data frame class as an object, which you assign to my_df. And the way that you specify the rows and columns is by giving this these column names and saying they are equal to some set of numbers or some set of characters or Booleans. And so these are the column names on the left here, and then these are the columns and the values in those columns on the right. If I add an extra one here, can anyone tell me what will happen and why? Okay, it gives an error. It gives an error. Let's take a look at that error. All right. Yeah, and exactly. So it's exactly what Lorena said. Manish, yeah, exactly. So when you make a data frame, one of the requirements is that all the columns are the same length. And so we've now made a column that has 4 elements, but the rest have 3. And so it gave us an error that basically says that. It says arguments imply differing numbers of rows, 4, 3. Okay. We can take a look at our data frame here, and now we've created it. It shows up here. We can click on it in RStudio and visualize it very nicely here. Okay. And we can also give it row names and column names that are different from the ones it had originally. So if we assign row names, we can do that quite easily using the row names function. And now it's got row names. You can see it automatically updates in this nice tiled or formatted view here. And we can change the column names as well. See, it's updated the column names now. Okay. You can also get to this view by running the view command in RStudio. Okay, so we can access data frames by using the row and column indices. So this is row 1, column 2, row 2, column 1, row 3, all columns. All right, all rows, but column 2. Now we can do this numerically, or we could do this with the actual names of those rows and columns, and we can mix and match as much as you want. So let's get row 1, which has the name row 1. We can see that right here. Okay, grabbing that, and we're grabbing the second column. So this is row 1, column 2, row 1, column 2, hello, hello. And so on and so forth. Row 1, column 3, row 2, column 1, row 2, all columns. Okay. You can also use the $sign to grab an entire column and grab it as a vector. So we're grabbing all of column 1 and returning it as that numeric vector. And we can grab the second element from it if we wanted row or column 2, row 2. Okay. So before we move on to lists, do you all have any questions about how data frames are working?
How did you get it to come up as a MyDF in that other place?
Right here?
Yeah.
So you just click on this here.
Okay.
Yeah, so once you create the data frame, you can just click it in this panel here, and it'll show up right there. You can also run this view command. The view command will also make it show up. Okay, any other questions about data frames? Okay, is there a way to overcome the error of missing values? I think there is, and still have a data frame. I think so. I mean, one of the things that you could do, we didn't talk about NA. So NA in R is kind of like, this says it's basically like not applicable. It's really not, oh, it is illogical. Okay, actually, I just learned this actually. So apparently NAs are considered a type of logical. That's insane. So NAs are a type of logical, and you can actually use them. Oh, this is very weird. I feel like even I'm learning something new about R right now. So let's say you've got 4 elements in the numerics and logicals column, but you only have 3 in characters. You could put an NA here, and that will allow you to construct the data frame even though you are missing a value. It's not technically missing, it's just NA. And NA is kind of interesting because NA is, I guess it says it's illogical, but you can use it with any data type. You can use it as kind of a placeholder for any data type. If I return now that characters column, I can see here that NA is still illogical here. It's not put it in quotes, so it's not a character. If I look at it, I can see it's not a character, it's a logic. It's you know what it was before. If I look at the class of it, oh, that's the answer. Okay, sorry, I just learned something really important. So what I said before about mixing data types is still true. It's just that when you take an NA and you mix it with some other character data type, it becomes a character behind the scenes, but it still looks the same, and you can still use it exactly the same as you were before. That's kind of wild. So data frames, all the columns of that data frame all have to be the same data type within the column, because that column is a vector, and all vectors have to be the same data type. It's just that when you make this, it converts the NA to a character. Yep, yeah, Simon, that's right. It becomes a character NA, but it still gets printed the exact same way as it was before. And I'm guessing you can also have numeric NA. I'm going to find that out right now. Yeah, and in fact, if you see it here, you can see the character NA has this weird double, carrots, sideways carrots with it. There's a name for that. Don't recall it, but the numeric one doesn't. If I look at the one in the numeric, it looks exactly the same as the one for the character when you print it, but if you look at the class, I bet it'll be, oh, sorry. I bet it'll be, yeah, it is a numeric. So it's a numeric NA. More you know. Okay, so sorry for that distraction there. It's just, because you can still constantly learn new stuff about how R works. Okay, so but the point is, if you want to construct something that has sort of an irregular shape, you can easily fill in those missing places with NA values. And that will allow you to construct that data frame just with the NAs in place. All right, awesome. All right, so let's take a look at lists now. Now, lists are a special data type because they can contain a combination of data types within them. Each element of the list, and you can see we're constructing our list here, each element can be totally different. And in fact, one of these could be an NA if we wanted to. If we construct my underscore list, here's another trick for RStudio. If you click on this, you can actually view it in RStudio. So you can see it here, and this is a nice way to view it. Okay, so if we print this, we can see it prints it as a list where the first element contains 1, second contains A, 3, true, 4, NA, 5 contains the vector containing 1, 2, and 3. So lists are a extremely versatile object in R, and once you get more advanced, you'll probably end up using them a lot because in many ways, they're actually a way for you to construct a totally customized R object that contains as many elements of as many different types as you want. And in fact, it can also contain lists. If instead of a vector here, or maybe in addition to it, I'll make also a list in here that contains 1, 2, and 3. And I'll also put in a data frame. I'll put in my df here. So you can see now when I print this to the screen, it contains here my list, and in element 6 now it contains a list. So that's why you see 6, 1. So this is the first element of the list that is inside of your larger list. And then 7 is a data frame, so it can contain data frames as well. So they're very, very flexible. You'll use them a lot once you get a little bit more advanced. You can also name a list. So let's revert this back to the way we had it before, so this code actually works correctly. So let's say that we actually only had 4 elements. Well, we can name those elements LM1, 2, 3, and 4 using the names command. And so now we can see here LM1, LM2, LM3, LM4. And we can access the elements of those lists using numeric indices like this. You have to put double brackets around it when you're using it as a list. Or you can access them by their name. Or you can use the $. As long as it's named, these last 2 will work. If it's not named, neither of these will work. Okay. Any questions about lists before we move on? Okay. Let's move on to matrices then. Now, we didn't talk about these in the lecture, but a matrix, all a matrix is it's vectors that have been stacked together. That is all it is. The vectors all have to be the same type. And so in many ways, it's quite similar to a data frame because it can have column names and it can have row names. But just know that in a matrix, all the data has to be the same type. So what we're doing here is we're making a matrix that contains the numbers 1 through 10. We're saying that there will be 2 rows and 5 columns, and we're saying by row equals true. And I'll show you in a second what that's actually doing here. So we can see we've constructed our matrix. It contains 1 through 10. And we can see that it has filled it in by going across the first row and then across the second row. If we set by row equal to false, we can see it went down the columns first, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, instead of across the rows. So that is what the by row command is doing. Like we said, you can have column names and row names. And you can access it the same way you would access a data frame. So data frames and matrices share a ton of similarities. Ultimately, matrices are a much more efficient object. So if you're trying to make your code really fast, really efficient, you'll want to use matrices. Ultimately, any sort of large scale mathematical calculations have to be done typically on a matrix or on a matrix in R. So you typically have to convert to a matrix before you can do that. Most functions won't really require you to do that. They'll do it themselves behind the scenes, but some of them will. So just pay attention to that. If something says that it requires a matrix, just know that you have to convert the data frame to a matrix and vice versa. Okay. Finally, let's talk very briefly about factors. Factors are very similar to vectors, except they have more information associated with them. So let's make a factor here that includes the vector 90, 80, 70, 60, 0. So let's say that these are grades. 90, 80, 70, 60, 0. So we can see it as a vector here, but now we can see it's actually got levels. So factors are essentially vectors where there's a particular order to the values in that vector. We can also add names to factors. So A, B, C, D, and F. So 90 is an A, 80 is a B, 70 is a C, 60 is a D, and then F is 0. So I guess we're trying to like associate letter grades with these now. And you can access them the same way as vectors. Now, the levels is kind of an important part because the levels will tell you the order that those values should be in. Now, we want our grades to go from 90 to 80 to 70 to 60 to 0. We don't want them in reverse order. We want to have the order be correct. So all we have to do is assign the levels as 90, 80, 70, 60, 0 to have them be in that correct order. And we can see now it is in that correct order. So just to show you why this kind of matters, I'll do everything up to here without actually doing that. So if I do, I think this is correct. This might not actually be a sufficient example to actually demonstrate this, but we'll see in a second here. Apparently doesn't like that. All right, well, forget that example then. Okay, let's do it this way. Yeah, all right, forget that example. In R4, I don't think this works. All right, just know that if you're ever trying to do something like you're trying to sort your data, so for example, if I wanted to, you know, sort, I don't know if I've shown you sort before, but if I want to sort my function, you can see here that if the levels go from 0 to 90, it'll put it in that order, 0 to 90. If I change my levels and I try now sorting it again, it puts it in the correct order. Although bear in mind that now it has the incorrect names. So factors are a little bit tricky. You kind of have to watch out for them. And in particular, I think that it's very unlikely you're going to end up doing much where you're going to really need them. So just know that they work. They're a little bit tricky. And if you ever find yourself needing to use them, to just be kind of careful how you use them. All right. That's my 2 cents on factors. Okay, so before we get with our last 15 minutes into intermediate concepts, again, we're going to go overtime. So if you need to leave, feel free to do that. But if you've got more questions and you want to hang around, do feel free to do that as well. I just want to make sure that we get to all your questions. So even if we go overtime, hopefully it will still be valuable. All right, so does anybody have any questions before we jump into the intermediate concepts? Okay. So let's jump now into vectors and vector comparisons, vector addition, that sort of thing. So let's take a vector here. It's got 1, 10, 4, and 5. If you add a 1 to that vector, what it's going to do is pairwise, it's going, or sorry, not pairwise, it's going to take that 1 and it's going to add it to every element of the vector. This is just scalar addition to a vector. So if you took linear algebra, this will probably feel kind of familiar to you. Now, if you take a second vector, you can do pairwise addition between your two vectors. Again, R tries to figure out what you wanted. So if you do an addition between two vectors of the same length and they're both numeric vectors, it will actually pairwise add every element together. Oh, okay, sorry. They're different lengths. I don't know why that happened. So it added them pairwise. Kind of funny. If they're different lengths and you try to do this, it will actually do it, but it'll throw an error at you. So just so you see here. And essentially what it does is it does the pairwise addition of each element. And then once it gets to the last one, it adds it to the first element, which is really, really not ideal. So I can't believe that it actually lets you get away with that. But yeah, that's not good. So make sure that if you see warnings like that, that you appropriately address them. All right, so that you get something like this. You can also do pairwise multiplication. Yeah, so let's try adding an NA in vector 2. It's a good question. Just gives you an NA. When you add an NA to anything else, it's still an NA. So yeah, that might be another way to deal with this. All right, so comparison works the same way. You can compare against a scalar, and that just goes through and it compares every value against that scalar value. So is 1 greater than 1? No. 10 is greater, 4 is greater, so that's why we get false, true, true. You can also compare against another vectors, and it'll do pairwise comparison. So in this case, it says 1 is not greater than 10, so it says false, but 10 is greater than 2 and 4 is greater than 3, so that's why you get false, true, and true. If we did it the other way, you see you get the opposite. You can also do pairwise equivalence, which none of them are equivalent, so you can see they're all different from each other. And same thing here. All right, so let's say right. So this is a really good point. So note, like Simon said, note that these comparisons yield a vector of logicals, which is not 3 separate logicals. As we've already said, though, that's actually the same thing. But yes, so it's important to note that. So if I say my logicals, if I set that equal to the result of vector 1 greater than vector 2, it yields back a logical vector here. You can see this here. My logicals is a logical vector of length 3 with false, true, true. So you can save that as a variable, and you can see it returns a vector here. All right, you can also negate a logical vector. So let's say that you've got this logical vector, vector 3. You can also negate it, and that will negate every element in it. Very good point, though. Yeah. It will still be a vector. Yeah, variables. Okay, so I didn't explain this, but variables are just giving a specific name to an object, right? You're just naming an object. You're not doing anything special to it. So when I take this object, true, false, true, this is an object. All I'm doing when I assign this to vector 3, I'm actually just naming this object with the name vector 3, so that in my global environment, this object is now stored under the name vec3. So yeah, that's all you're doing. Anything can be assigned, anything can be saved as a variable, because all you're actually doing is taking an object in R and assigning a specific name to it. And now vec3, the name vec3 is specifically associated to this object. So without getting into how this works in memory, because basically this is related to how R works in memory, that's what it's doing. So vec3 contains this. And that's why if you say vec3 is equivalent to the thing you originally assigned to it, it says true, true, true. Yeah, okay. All right, so let's say vec4 is false, true, true. If I say vec3 and vec4, it's going to do a pairwise comparison. So it'll say true and false. We know that is false because both sides of an and have to be true for the whole thing to be true. False and true, again, that's all false because the whole thing has to be true. And then true and true, both of those are true. Therefore, the whole statement will be true. And now we can see that right here. False, false, true. Or same thing, but only one side has to be true. Therefore, when we do this, all three are true. All right, same thing works with characters. Yeah, I'm not gonna belabor this anymore because I think this is probably beating a dead horse at this point. But you can see here you can do the same scalar in air quotes and pairwise comparisons with character data types as well. Okay, finally, let's get into the in operator and the which operator. So in between percent signs is not the same thing as in like a for loop. This is actually a logical a logical comparison operator. And what it's going to do is it's going to take some scalar or length one character or length one logical vector, some logical, some character, or some numeric, and then it's going to find if that is inside of another vector. All right, so is 11 in 1 through 10? Well, we know that that's not true. So it gives false. Is 5 in 1 through 10? And we know that that is in fact true. Is true in true, false, false? True, because there is a true in true, false, false. Is hello in hello world exclamation points? And in fact, we know that is true because you can see it right here. What will line 256 give me? Can anyone tell me what that will evaluate to? Good. It'll be true because it negates. Exactly. So aloha is not in hello world, but because of the negation, it gets reversed from false to true. All right. So let's take a look at this here. We're saying 1 through 10 equals 5, which means that only the element that equals 5 will be true. So we get false, 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 true, false, 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 false. Now, the which statement is going to take this logical vector and it's going to return the indices of all the elements of that logical vector which are true. Okay, so it's going to find which of these is true. It's going to see that it's index number 5, and it's going to return that. And we can see that's what it's done here. So which is a handy way to convert between a logical vector and a numeric vector that gives the indices which are true. All right, so there's another function of interest, which is the length function. So length just tells you how long a vector is. You can see this is a length 5 vector because it's got 5 elements. The sample function is going to randomly select some number of elements from a vector and return them. So if I've got a vector of 1 through 100, if I sample that vector and I say that size is equal to 10, it's going to randomly find 10 variables from that vector, or 10 values from that vector. So it randomly selected 10 values from my vector of numbers from 1 to 100. when you start doing things like bootstrapping, this is a very useful, well, yeah, they should be different. Yeah, so the values you get when you run this should be different because this is working based on randomness. So it's randomly selecting every time. Okay. Yeah, pretty cool. You can actually control that behavior by saying set.seed. You can set a random seed. So I'm saying set.seed 42. And now every time I run this, it'll give me the same results. Whereas before, if I don't set that seed, it'll give me a different result every time. If I set the seed first, it'll give me the same results every time. And that's because the seed is part of the random number generator that controls how the randomness actually works in R. And so if you set the seed, it is random in theory, but you can actually get the same random result every time. It's a cool trick. All right, let's talk about a numeric vector now. Let's say we want to find the maximum value in this vector. We would use the max function. So max of my nums will give the max value. So we got the max here. The max is 100. That's the largest number here. Min is the smallest. Mean is the average. Median is the median. Sum is the sum of all the numbers. SD is the standard deviation. And so that's how you can get your sort of descriptive statistics on a distribution, which we can represent in R. We can represent distributions of values as numeric vectors very easily in R. All right, so I know that we're definitely going over time here. Again, feel free to leave if you have got something else you need to do. This will all be online later. But for anyone who wants to stick around, we'll be here probably another 30 minutes, and we'll answer some questions about if-else logic, and also functions, for loops, and the apply family. All right, so before we move on, does anybody have any questions about what we've covered so far? Everything with if-else, functions, loops, all of this builds on what we've shown so far. As you can see here, we're already looking at, we're doing if-else here. We can already see there's our logical comparison right there. So understanding how logical comparisons, that sort of thing, works is really important to being able to understand how the rest of this is working. Okay. So let's go ahead through if statements now. So we're saying here I is equal to 4. If I is greater than 5, we're going to print I is greater than 5. So basically, this is the structure of all if-else statements. You've got some logical operation that can only return true or false. And then if it returns true, the code between the brackets gets run. If it returns false, the code between the brackets does not get run. All right, so I is not greater than 5. If I take this and I run it in the console by hitting Control Enter, having highlighted it, we can see it returns false. Therefore, this code should not be run. And we see it's not run. If I change I to 40 instead, we can see now it is greater than 5. And so this code will be run. And in fact, that's what we see. I is greater than 5. All right, so an else statement is going to be run when the first part did not evaluate to true. When anything above it, actually, I'll say this more broadly, when everything above it did not evaluate to true, then the else statement will be run. So I is equal to 4. We already know that I is not greater than 5. Therefore, this will not get run. And because of this, our else statement will kick in and it will execute the code print I is not greater than 5. Now, again, if this was 40 instead, this first part would get run because now this evaluates to true. So therefore, this part would get run, and this part will be ignored. Because once you run some part of your once you run some part of your if else statement, the rest of it gets ignored. And so we see it prints I is greater than 5. So now expanding on that with if else, we're actually just doing the same thing we were already doing, except we're starting to chain these together. So essentially what this means is that we're going to run the first part. If I is greater than 0, we're going to print I is positive. If this ends up being false, let's take a look here. It is false. So if this ends up being false, which it is, this will not be executed. And instead, we're going to move on to our else if. So else if I is equal to 0. So now if this first part didn't get run, but this is true, which it is, then we will execute this second statement and ignore the rest. Now, if both the if and the if else and the else if statements are false, then we'll proceed down to the bottom and run our else statement. So it says I is 0. It's exactly what we expected. If I set I to -2, we now know that this is false and this is false. Therefore, it will run the else section. Okay, so you can see it runs that. All right, does anybody have any questions about how this is working? Okay, all right, good. So just bear in mind, like everything in R, you can mix and match as much as you want. So I could easily include, I could include another if else in here. So let's say I didn't want to just print I is negative. Let's say I wanted to print, I is less than. So let's add another if else in here. So let's say that if I is negative, which means my else will get executed. Let's add another if else here. If I is actually less than -5, I'm going to print I is less than -5. Else I is between -5 and 0. And I know this is true because to even get to here in the first place, I has to be negative. Okay. So that's how I know that if I is not less than -5, it has to be between -5 and 0. So we'll set I to be -1, and we can see it prints I is between -5 and 0. If we set it to -6, we can see it says I is less than -5. All right. Just so you can see how you can start chaining these together to make more complicated and interesting logical blocks. All right, so let's go to the loops now. So when we talk about for loops, we're talking about a finite loop as opposed to while loops, which are an infinite loop. So let's talk about finite loops first. Those are for loops. So let's take our days of the week, Monday through Sunday, and we'll loop through them. We're going to say for day in days of the week, print day. So it goes Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And like we said earlier, we're taking our vector that contains the days of the week, we're looping through it, and for every element in the vector, we're going to take that element, assign it to day in order, and then execute the code between the brackets. So we'll do something with that variable typically. So day is constantly being reassigned every iteration. So every next step in the loop, you're assigning day to be that day of the week. All right, so that's one way of doing loops. Then I think in DataCamp, I call that type 1. Type 2, which is actually not different, it's just, it seems different, but it's actually not, is to do this sort of I in 1 through length days of the week. So if we look at this 1 through length days of the week, that just gives us 1 through 7, because that's the number of elements in our vector here. And length, if you recall, tells us how many elements are in a vector. When you use this sign, that gives you the length, or it gives you the vector containing all the numbers between the number you start with and the number you end at. And so I is being reassigned to one of these numbers each time. So let's say that we're going the first time through the list, I is equal to 1. And so if I is equal to 1, then the day will be Monday. So we subset our vector using I, and we can see if I is equal to 1, then days of the week of 1 is Monday. So it works the same way. It gives you the same results ultimately. It's just nice to have this I, because let's say that there was another vector, test vector. Let's initialize an empty vector here. So this is how we make an empty vector. Just take a look at it here. You can see it's an empty vector. It says null. All right, so let's say that if day is equal to Saturday, test vec of I is party. Else no party. So let's say we're testing here. Oops, I accidentally put the wrong kind of bracket. Sorry about that. So what we're doing is we're now adding a little bit of logic. And we're saying if the day happens to be Saturday, we're going to take test vec, and whatever that position that I is in test vec, we're going to assign that to the value party. If it's not Saturday, we're going to assign that to the value no party. And so what we should end up with is, for test vec, a vector that's the same length as days of the week, but includes the values either party or no party. So let's go ahead and run this now. So we printed all of our days of the week, and we can see now test vec says party, 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 or sorry, no party, except on Saturday it said party, and then on, it said no party. And just to show you why, there is some actual practical application of this, we'll make a data frame, and we'll add in here days of the week, and we'll add in here test vec. Notice I'm not assigning column names, because you don't actually have to if you don't want to. You can just give a set of vectors. So now I've made test underscore df. If I take a look here at this, I can see it's got Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and then it says here on the right whether there's a party. So this is kind of a nice way to be able to see it. You can see the column names, what it gave as the column names were actually the names of the variables that held those vectors. So you can see here days of the week in test vec became the column names. That's just R trying to think for you. Typically, you'll actually assign column names yourself, so don't worry about that too much. All right. Does anybody have any questions about what I just did there, or about how these loops are working? So why I? The reason is because, let's say you wanted to do something with, so let's say that you're, like I'm saying here, like let's say you're building some sort of new vector that you want to be the same length as your original vector, days of the week. So let's say you've got days of the week, that's a vector. Test vector is the new vector you want to build. You want it to be the same length as test vector. Yeah. And you want the index of days of the week to match the index of test vector, so that when you combine them into a data frame, they're matched up correctly. So 1 corresponds to 1, 2 corresponds to 2. Yeah. And that's how you get Saturday is party time. Manish asks, how do you type the assignment symbol so quickly? There is a shortcut, and the shortcut is Alt minus. Yeah, you just have to hit Alt minus on Windows. I have no idea what the shortcut on Mac is. Sorry. I know there's a shortcut on Mac. I just don't know what it is. I'll make the case to you later on why I think you should always use the assignment operator and not use the equal sign. Because I know not everyone agrees about that, but there is a good reason to do it. And I will briefly make that case at some points during this workshop. At the very least, it will be the proper way. All right, were there any other questions about the for loops? All right, let's move on briefly to while loops. So for loops are a finite loop, and that's because, as you can see here, it can only ever go as long as the total length of days of the week, right? So if days of the week is 1 billion, that's fine, but it means that the for loop can never go to 1,000,000,001. Okay, so just keep that in mind, that for loops are finite because they're based on the length of the vector that you give in this, something in something statement here. While loops are infinite, which means that they will keep going until some condition is met. So this is the condition that while this is true, it will keep going infinitely. Okay, so I said x is equal to 5 here. While x is greater than 0, we're going to print x, and then we're going to subtract 1 from x. And then after 5, I think, iterations, x will be 0, and then this will no longer be true. So that's how we stop the loop. Okay. So you can see here it went 5, 4, 3, 2, 1. When x got to 0, which you can see x is now equal to 0, this was no longer true. See, it's now false, and therefore the loop stopped going. So that stopped the loop. Does anyone know what would happen if I took out this line? I really recommend not doing this, actually. Don't do this. If don't run this yourself. I'll show you just so you can see what happens, but don't actually do it yourself. Okay. Does anyone know what will happen? Yeah, you'll learn the hotkey to manually abort an R script. Yeah, that is exactly what will happen. You'll learn how to open up Task Manager is what will happen. Yeah, all right, so let's show this here. All right, hopefully Zoom keeps working while this happens. So we've taken out the statement that reduces the value of x every time. Therefore, x will never reduce in value, and therefore this condition will always be true. Infinite loop. So now we've got an infinite loop. You can actually stop this pretty easily. You kind of want to do that quickly before R crashes. So you can either hit the stop button or hit the escape key. Or, yeah, escape key. And it will stop. Just whenever this happens, if you ever do while loops, not that I'm saying there's a good reason to do while loops. There's typically not any good reason to use these. But if you do find a good reason to use one and you run into this problem, you can always hit the escape key. Usually. Sometimes you can't, and then you have to learn how Task Manager works. All right. Okay, so we're going to combine if-else and for loops here in this example. So I didn't realize I'd written this example. If you run through this, you can see this is actually kind of similar to what we showed before. If the day is Saturday, then we're going to print party time. If the day is Monday, we're going to say I hate Mondays. And if none of those are true, we're going to say no parties today. So it says Monday, I hate Mondays. Tuesday, no parties. Saturday, party time. Sundays, no parties. So just showing you how you can combine for loops and if else. All right. Functions, those are a pretty complicated object type in R. They can be pretty infinitely customizable. Just know that in their most basic form, functions are defined like this. You're going to make the function using this command here. This is your constructor. This constructs the function object, and then you're going to assign it to some name. So you can actually run this without assigning it. It just returns it as it prints it to the screen like this. But typically you'll want to assign it to a name. And now you can see my funct down here on the bottom has been created. If you click on this, you can actually see it in R. Anyways, so this function is going to take a number as an argument, and then it's going to print that number to the screen with a little message. So we're going to give it the number 100, and it says your number is 100. So the way functions are essentially working is that you specify arguments, and then those are variables that can be used within the function. So if I specified another argument here, you know, party, let's say, yeah, day. So if I specify this argument down here, day, and then I add a little bit more logic in here. If day is Saturday, if day is Monday, if else, you know, print no parties. So I'm adding this logic in here as well. So now I've got two arguments in this function. Does anybody know what will happen if I try to run line 373 now? Without specifying a day? Well, for the sake of time, I'll just show you here. I'll just show you. It says error, argument day is missing with no default. Basically, if you don't have some default argument for day and you don't give it when you're trying to call the function, then it'll error. Now, I could specify a default, but let's show how you can do this without doing that at first. So, okay, so if you're in a function and you want to know what arguments it contains, you can just hit tab and it'll tell you what the arguments you can supply it are. So let's say I want to supply it with its number, 100, day is Saturday, and now it works. Also notice that you don't have to do this number equals 100. You can also provide it positionally like this. That'll still work the same. And that's because R knows that you give number first and then day. So if you give an argument without specifying what, or if you give a value without specifying what argument it belongs to, it'll check the position. So if it's in the first position, it'll assume that's the number. If it's in the second, it'll assume that's the day, because that's the order that you specified it when you defined the function. So this still works. It's typically better practice to not specify arguments positionally, because now you're explicitly saying what you want it to be, and you can avoid any potential confusion. Now, a function can have a default argument. This is how you would specify that. Now, what this is going to do is if you do not specify the day as being Saturday, it will, I'll just to illustrate, I'll put Monday here. If you don't specify what day of the week it is, it will assume you want the day of the week to be Monday, and it will use the value Monday by default as the variable day. And so you can see here that worked. It said that it was Monday, and it said, I hate Mondays. But if we override that by giving the day being equal to Saturday, we can overwrite that and it says party time. Is it because it's the first element? Is which Monday? No, it doesn't matter. It literally doesn't matter. It can be Tuesday. You can just do whatever you want here. So if I say day is Tuesday by default, I'll erase this again and run this. It'll say no parties today. it didn't choose Monday automatically. It's because I said the default was Monday. If I set the default equal to Monday, then if you don't supply a value for Monday to the function, it will just assume this is the one you wanted. Yeah, exactly. Yeah, you don't have to supply. I mean, I'm sure you'll see this very quickly as you start working with functions in R, but when you don't supply a value to every argument in a function, that doesn't mean that the function is not going to work. It's because it has default arguments that it still works. Okay. All right, and so we made this other function here, random picker, which can randomly pick some value from a list. So if I run this on days of the week, it'll randomly pick a day, a value, or one of the values from days of the week. And you can see it picks Friday, it picks Saturday, Thursday, randomly picking, because all it's doing is sampling days of the week and selecting one element from it randomly and returning that element. So that's one thing I didn't mention, which I'll just very briefly touch on. So this function just prints, my funct just prints out a statement. But you can also have a function return a value, which is in many cases more useful than actually just printing something. So if I run this function, it'll return the value that is the result from randomly picking a day of the week. So we can see here, it actually returns Sunday as the randomly selected day of the week, which we've assigned to the variable my results. And you can see it's changing every time we run this. To actually return that value, all you got to do is use the return command on the object you want to return from the function. All right. I know I breezed through all of that. Hopefully this is making sense. Before I just touch very briefly on the apply family, does anybody have any questions about what we've seen so far? Okay. So final part is the apply family. So with the apply family of functions, you can apply a function across some object. So typically, when you do this, you're going to be doing it to a vector. So days of the week is a vector. We want to apply a function to every element of that vector. Let's say that the function we want to apply is our, sort of if-else statement here. If the day is Saturday, we return the statement party time. Monday, return I hate Mondays. Else, return no parties today. Now, sapply in particular is going to return those results as a vector. So if we go ahead and run this here, we can see it returned the results as a vector. For Monday, it said, I hate Mondays. For Tuesdays, it said no parties today. Wednesday, no parties today. And you can see that it returns the vector, and then the names of the vector are the original days of the week we supplied to it. So you can do this a couple ways. You could consider this to be an anonymous function because we didn't name this function. We didn't name this. This is just supplied anonymously to the sapply function. We could have also named the function, and that's what we're doing up here. We can name it my underscore function, and then we could just replace this with my underscore function, and it will work the same way. So it can be named or it can be unnamed. It doesn't matter. lapply does the exact same thing that sapply does, except that it returns its results not as a vector, but as a list. So we're going to do the exact same thing. And we'll just take a look at the list that returned. So it says, I hate Mondays, no parties today, party time, no parties today. So same thing, just returns it as a list instead. And we can actually assign the days of the week as the names of that list. And then you'll see here when we refresh this, now it says Monday, I hate Mondays, Tuesday, no parties today, so on and so forth. All right. So finally, apply works on matrices, but actually it works on vectors as well. It just does it in a sneaky way. So don't worry about the difference between using apply and like sapply and lapply for right now. Just know that the main thing that's going to really be functionally different from them is that you're returning either a list or a vector or a matrix as the result. So apply returns a matrix as the result, but it actually operates on vectors, even if it doesn't seem like it. So let's make our matrix here. We're going to say my_mat, and we're going to apply a function to it. We're going to say the function is number. If the number is greater than 5, we're going to say true. Else, we're going to say false. And margin 1, 2 says we want to look at rows and columns. If we said margin 1, it would only look at rows. If we said margin equals 2, it would only do it to columns. But we're going to do it to rows and columns. And if this seems confusing, don't worry about this right now. It's unlikely you're going to use apply at any point in the near future. But just, I want you to get the intuition of how this is working. So what does our result look like? It looks like false, 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 true, true, false, false, true, true, true. And this matches up with our data here. If it's greater than 5, it's true. And we can see everything after 5 is true. All right. We can also apply this across columns, which I kind of demonstrate very briefly here. So we're going to sum every column. Okay, so it's taking each column as a vector and it's applying the sum function to them. So it added up the first column, 1 and 2 makes 3, 3 and 4 makes 7, 5 and 6 makes 11, and so on. And then finally, you can do the same thing except across rows. So it'll sum across the rows. And now we've got our 2 rows. So okay, what was it? 1, 3, 5, 7, and 9. When you add these together, you get 25. 2, 4, 6, 8, 10. When you add those together, you get 30. And that is, in essence, how apply is working. So hopefully this was helpful. Does anybody have any sort of final questions here about what we've covered, or any I guess concerns about the material? I know this is hard. Like, this is definitely the hardest part. So if you've got questions, do feel free to ask those now. Okay, so the last thing that I wanted to mention is that there's a really great assessment on DataCamp that I want you all to do, which is going to essentially rate your degree of skill in R programming. Now, it's a sort of reactive assessment in the sense that the better you do on it, the harder it's going to get in response to how well you're doing. If you are not doing as well, it will make the questions less difficult to give you more of a chance. You can do it whenever you want. There's no, it's like the assignment expired today. It doesn't matter though. You can do it at any point. And I would recommend that you definitely do that when you get a chance, because it'll teach you about where you have shortcomings in your capabilities with R programming. And it will also give you a strong sense of what you need to improve on. The last thing that I wanted to mention is that I recently created this challenge problem for something unrelated to this. And I would recommend checking it out. And you can see here, I'll just put the link here. It's got some very basic I guess, instructions here. And basically what it's asking you to do is to create a game of tic-tac-toe with R. So you'll create an R script that will allow you to play tic-tac-toe against the computer. And so I'm actually showing here the one that I made. You can run it with the R script command on the command line. So that would basically be, if you go here to the terminal, that would be where you would R script, and then you would put the name of your R script here and run it. But anyways, so this is a great challenge, and I'm offering a prize. So anyone who actually completes this and gets it completely correct before the next one, you can send it to me. I'll review it and let you know if it's not correct. I'll let you know where errors are. But if you do this and you get it completely correct, there will be a prize. So it's a little bit of added incentive there. All right. With all that, yeah, we'll see you all in 2 weeks for the Tidyverse lesson. And yeah, feel free to attend the office hours, and feel free to send an email if you've got any further questions or you run into any issues with anything we talked about today. All right. You all have a good week, and I will see you next time.